Hello, everybody. It's Mrs. King here. Um, Not sure when you're watching this. I think it depends on if you're a red or a blue kid, but I'm recording this on Monday, our snow day. I don't really know what snow days mean anymore, but hope you're all staying warm. So this is a video for section 3.6, and it's on position, velocity, and acceleration. And we call them SVA problems because S is for position, velocity, V, and A for acceleration. Now, every year kids ask me why we use S for position, and I usually make up something. But I actually found out that, well, I knew why we didn't use P. We don't use P because P tends to be for probability instead. So that's why we don't use P. But I found out that the reason why we use S is because the position that we're talking about is the position in space. And so then S for space. So, fun fact of the day. There are different types of SVA problems, and one of them is vertical motion or projectile motion. You may recall learning that in Algebra 2, because all projectile motion is like when you kick a ball or launch a rocket or throw something. Your position function is actually a height function dependent on time. And then the negative 16t squared, the negative 16 has to do with the acceleration due to gravity in feet per second. And then plus your initial velocity times time, plus your initial height. Maybe that looks familiar. You don't need to know that, but it's an Algebra 2 problem. And you can use all Algebra 2 skills to answer questions about projectile motion. So what we're going to talk about, though, is horizontal motion, which is when you have a point that's like moving horizontally left and right at different velocities back and forth on this horizontal line. So that's what we're going to talk about. There's other kinds of SVA problems when some other equation is given, but like all of the stuff that we find would be the same. So really we're just going to focus on this horizontal motion today. You have a note page for this in your workbook. It's after worksheet 3.5, but before 3.6, and I'll be using that note sheet for this video. So we've got this position function. It's given to you as S of t, and it's this cubic, 2t cubed minus 9t squared plus 12t plus 1. That's your position function. Notice that they also give you a domain restriction. So the time that this particle is moving, the time is from -3 to +3. So we want to find the velocity of our function. The velocity is just the derivative of position. So 6t squared minus 18t plus 12. And so like I said, that's just the derivative of position. And then we can also find the acceleration, and that's just the derivative of velocity. So take the derivative of velocity and we get 12t minus 18. So that's the second derivative of position or the first derivative of velocity, either way you want to think about it. All right, so now there's like a ton of stuff that you can be asked about this particle that's moving back and forth on this number line. The first thing is the displacement. Now, what displacement means is, this particle is moving left and right, and changing directions and going different distances at different velocities and all that kind of stuff. But the displacement is really asking, like, okay, wherever the particle is at a time of 0, it does its thing for 3 seconds. I don't know if it's seconds, I'm making that up, for 3 units of time. And then after those 3 units of time, it's at a different position. So what's the difference in positions for, like that's what displacement means, the difference in the two positions. So we are going to calculate S of 3 and then minus S of 0. Okay, now I went and tried to open up my calculator on my computer and the license has expired. So I'm using my calculator right now. And what I've done is in my Y1, I've put my position function in. And so then if you can recall, if you hit alpha trace, or that's the same thing as the F4 shortcut, you can select Y1 and then do like function notation, and you get a position of 10. And then you can find the position at a time of 0, which is 1. And so subtract those and your displacement is 9. So what that means is that this particle has like the difference in its positions over these 3 units of time is just 9 units. Okay, who cares what its journey was, but just its positions at those 2 times is all you're looking at. Okay, all right, now average velocity. If you think back to some other average things that we've done, average velocity is an average rate of change of position, right? It's an average rate of change of position. So we're not finding the average velocities at a time of 0 and a time of 3. That's not what you're doing, okay? You are not, I'm going to say this one more time. You are not finding the velocity at 0 and the velocity at 3 and averaging them, okay? You're not doing that. Instead, it's an average rate of change of position, okay? So an average rate of change is the same thing as slope, right? Average rate of change is slope. So then it's the slope of position from a time of 0 to a time of 3. So we're going to find the position at 3, subtract it from the position at 0, and divided by 3 minus 0. Okay, I always translate words like I'm trying to do with you. An average velocity is an average rate of change of position. So then average rate of change means slope. Okay, slope of position. So now to calculate this, I've already got the numerator is 10 minus 1. So 9 over 3 is 3. Okay, now find when the particle is to the right and to the left of the origin. This is talking about position as well, because if you're talking about the right and left side of the origin, that's all the position of the particle. So what we're going to do, we are going to find when the position is negative, because that means that that's when the particle is to the left of the origin. And we're also going to find out when the position is positive, that's when the particle is to the right of the origin. Now that means we need to do a sign chart. Okay, so unfortunately, since I don't have my calculator on my computer, I can't show you and remind you how to do these sign charts. But what I would do is I would graph your position function. And I would restrict my window to just x values, which are the same thing as time, from -3 to 3. That means that I would also restrict my sign chart to that domain. Okay, then once you get your graph, you're going to go to second calc and find the x-intercepts. And then that x-intercept is -0.078. Again, you can round or truncate. The cubic has negative values to the left of that, and then it has positive values to the right of that. So there's my sign chart. And so that means that when my position is negative, so at the times -3 to -0.078, that's when the particle is to the left of the origin. Ah, come on. So it's to the left from -3 to -0.078 units of time. and then it's to the right of the origin when your position values are positive. So from negative 0.078 to 3. And I realize I just made a mistake, so let me fix it. The position is equal to 0, right? The position is equal to 0 at this negative 0.078. So that means that the particle is at the origin at that time. It's at the origin, it's not to the left or to the right of the origin. So we want to use parentheses on that. Now I can use parentheses, or I can use brackets on the negative 3 and 3 because my function is still negative when the time is negative 3, and my function is still positive when the time is positive 3. Okay, next thing is when our particle is moving to the right or to the left. Now here's a key word right here, moves. If we're talking about something moving and it's movement, then we're talking about velocity. Okay, so when your velocity has positive values, then that means your particle is moving to the right, and if it has negative values, then it's moving to the left. If your velocity equals 0, that means that the particle is not moving. Okay, so what we need to do is now we need to make a sign chart for our velocity function. So now this one, you could graph. Again, there's nothing wrong with that. You could graph this quadratic and find the x-intercepts. You could also, I believe, factor this. Oh, what am I doing? I could factor out a 6. Oh yeah, we can factor. So what, t minus 2 and t minus 1. So that means on my sign chart, I still want to cut off my domain, right, from negative 3 to 3, and then I have x-intercepts at 1 and at 2. And then, if I'm not graphing it, I know what this quadratic looks like. It opens up, so it goes plus, minus, plus. If you use your graphing calculator, that's totally fine. But now I can use that sign chart, and I can answer the questions. It's moving to the left over the interval 1 to 2. And again, I'm not going to include either of those because that's when the particle is not moving. And then the particle is moving right from negative 3 to 1 and from 2 to 3. Oh, don't use the 1. Okay. All right, so now things get interesting. Find when the particle's speed is increasing or decreasing. So speed is velocity, but without the direction. Okay, speed is velocity, but without the direction. So if your velocity is positive, then that means your particle is moving to the right. So then if that is increasing, that means that the derivative, which is acceleration, needs to be positive. Okay, now it works the same if the velocity is negative. That means that your particle is moving to the left. And so then if that's increasing, then it needs to be accelerating to the left as well. That's what makes the speed increasing. You can also think about, I don't know, like a runner. If you're outside running, then if the runner's running in one direction, that's its velocity. If the wind is behind him and blowing in the same direction that he's running in, then his speed will increase. And so it doesn't matter if the runner like which way the runner's running on the track, as long as the wind is behind him and going in the same direction. Okay. And so then if the speed is decreasing, that would be like the runner is running into the wind. So the runner's direction is the opposite of the wind's direction. So your velocity and acceleration would be different signs. One's positive and one's negative. If you've ever driven a boat, you throw the boat in reverse if you want to slow down. Okay, if you want your speed to decrease, you put the boat in reverse. Okay, so that means that the direction that you're going in, your velocity, and then putting it in reverse is your acceleration. Those would be opposite directions. That's what slows you down. Okay. All right. So what we have to do is we have to compare velocity and acceleration sign charts. So now let me take a quick second and make my acceleration sign chart. Same domain restrictions. And then you could use your calculator on this too, or add the 18 divided by 12. 18 over 12 reduces to 3/2 maybe. I think so. Yeah. 6 over 3 over 2. Yeah, 1.5. So then 1.5 is your acceleration, x-intercept. It's a line with a positive slope. So that is what that looks like. Now we compare these and we look for where, like let's say we want to answer the question, that our speed is increasing. So for our speed to be increasing, then velocity and acceleration have the same sign. They're working together in the same direction. So we compare and we find areas where they're both negative or they're both positive. So if you can see here, the little parts that I just highlighted in yellow, from 1 to 1.5, both velocity and acceleration are negative. Okay, so from 1 to 1.5. And then again, from 2 to 3, they're both positive. Okay, so those are two intervals of time where the velocity and acceleration have the same sign, which means they're going in the same direction, which means your speed is increasing. Okay, so from 1 to 1.5 and from 2 to 3. Ooh, come on. From 1 to 1.5 and from 2 to 3. The 3 I could put a bracket on. Okay, now the speed is decreasing when your velocity and acceleration are opposite signs. Doesn't matter which one's positive and which one's negative, but they will be opposite signs. So again, compare the velocity and acceleration and find intervals where they're different. So from -3 to 1, they have opposite signs. From 1.5 to 2, they also have opposite signs. So that's when the speed of the particle is decreasing. Okay, -3 to 1 and 1.5 to 2. All right, last but not least, find the times when the particle is moving towards the origin. All right, two big words here. Moving would imply velocity, right? Moving implies velocity, so we're going to have to look at velocity. But then towards the origin implies where the particle is. So that's the position. So now we are going to involve position and velocity. Okay, now these two things make sense. Let me draw you a quick number line and explain it. Let's say here's the origin. If your particle is on the left side, then that means that its position, I just used P, that means that its position is negative. If it's moving towards the origin, then it has to be moving to the right, which means that its velocity would be positive. Okay, so we're going to look for places where the position and the velocity are opposite signs. I promise you it's opposite because now look at the other side. If your particle was over here, that means your position is positive, and if it's moving towards the origin, it would have to move to the left, which means your velocity is negative. Okay, so towards the origin, we're going to look for opposite signs on position and velocity. So look at your position and velocity sign charts. Your position and velocity sign charts have opposite signs from -3 to this -0.078, okay? And then after that, position's always positive. So then again, from 1 to 2, they have opposite signs. Okay, position and velocity have opposite signs, -3 to the -0.078, and again from 1 to 2. That's an 8. All right, now what about when position and velocity have the same signs? If they have the same signs, which this question didn't ask about, but let's talk about it because it says it right here. If they have the same sign, then that means that your particle, let's say it's on the right, that means its position is positive. So the same sign means that the velocity would be positive too, which means it would move to the right. So that's moving away from the origin. Same thing if you talk about the left. If your particle's on the left, your position is negative. Well, if your velocity is also negative, it's moving to the left and it's moving away from the origin. Okay, so you could be asked either. You could be asked when's the particle moving away from the origin or when it's moving towards. All right, so that pretty much sums everything up. Here's kind of a big recap of all of the stuff that you could be asked. This is not all of it yet, but you know, the position, okay? The position is positive, or it's equal to 0, or it's less than 0. And so that's where the particle is, to the right of the origin, at the origin, or to the left of the origin. Then we've got our velocity, that's the movement of the particle. It's either moving right, or it's not moving at all, or it's moving left. And then the acceleration, A, again, it's positive, equals 0, or less than 0. And so it's accelerating right, not accelerating, or accelerating left. Then the harder ones that we just talked about there at the end are right here. When you compare velocity and acceleration, then you're looking at if the speed is increasing or decreasing. Okay, if the velocity and acceleration have the same sign, means they're working together, so the speed is increasing. We compare position and velocity when we're moving towards or away from the origin. And you know, if they've got opposite signs, one's on the right but moving to the left, that would be towards the origin. Okay, so that's basically everything that we just covered. Now you are capable of completing worksheet 3.6. I do want to take a look at worksheet 3.6 real fast though, just to make sure that you are good to go and comfortable. Number 1 is not the horizontal particle motion. It talks about an automobile running down the hill. That's okay. It says, what are the velocity and acceleration after 1 second, 2 seconds, and when will its velocity be 28 feet per second? You're given this position function, go ahead, take the derivative, find velocity, take the derivative again, find acceleration. What are the velocity and acceleration after 1 second? You're going to find v of 1 and a of 1. And then after 2 seconds, you're going to find v of 2 and a of 2. Okay, and then when will the velocity be 28? You're going to set your velocity equation equal to 28 and solve for t. Okay, hopefully that's straightforward, but it's nothing like what we just did in the notes. All right, now number two doesn't give you the equation so that you can, the position equation so that you can find velocity and acceleration, but that's okay. Translate this. At a time of 0, the particle's position is 5, right? At a time of 0, the particle's position is 5. That means that s of 0 equals 5. The particle moves to the right for 3 seconds and ends up at a position of 11. So that means the position after 3 seconds is 11. Then the particle turns around and moves left for 4 seconds. So now we're at a time of 7, right? We're at a time of 7. So it's because it's the 3 plus 4, and that's now at a position of 3. So you know these things, okay? You know those. The displacement, it's asking the displacement from a time of 0 to the end, the time of 7, just to clarify that. And now the total distance traveled, go ahead and figure that out. You want the total distance, not just the difference from the start and the end, but that whole distance that the particle traveled. All right, then problems 3, 4, and 5 are much more straightforward, just like what we did. You're finding displacement, average velocity, the velocity and acceleration, instantaneous velocity, that just means the velocity of 3. When the particle is to the right and left of the origin, when it's moving right and left, and when your speed is increasing and decreasing. All stuff that we just did. I want you to be aware that on problems 6, 7, and 8, you are supposed to justify on these last 3 things. Your justification is going to be stuff like because the velocity is negative there, or because the velocity and acceleration have the same signs, or whatever. They're all like your justifications are basically all of these things and all of these things. Okay, like those are the types of justifications that you'll write down. But you only need to justify for those last 3 problems, parts C, D, and E. Okay? All right, now you are good to go for 3.6.